Hello and welcome you all to the fifth lecture of the course on Standard Model of Particle Physics. And in today's lecture, we are going to talk about something very important, and that is called the cross section. Now, you remember that in the previous lecture, we actually developed the idea of the decay width of a particle, and we also developed this idea of Lorentz invariant phase space, and that is going to help us to actually define the cross section, but we need something more, which we are going to define as we go along. But before we start, let me remind you that why cross section is important, because see, in particle physics we are mainly going to talk about the fundamental particles of the universe and how do they talk to each other, what are the fundamental interactions through which they interact. And for this collision of particles, interaction of the particles to produce a bunch of other stuff is something which is going to be of paramount importance. Okay? So, we are going to look into the detector, look into the final state particles they have produced, and from that we are going to infer what kind of interactions that particle actually underwent. And this is how the particle physics have been developed so far. So, let us get started with the definition of what we call the cross sections, which in a collision of particles. Okay? So, unlike the decay width, the interaction cross section basically depends on something called the flux, that is the number of particles which are essentially crossing unit area per unit time. So, this is the definition of flux, which says that how many number of particles are crossing unit area per unit time. And of course, in a cross section we are typically going to talk about something like you have A and B type of particles are colliding and producing a bunch of stuff 1 plus 2 plus 3 plus dot 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 n, many final state particles. Now, let us consider a beam of particle of type A with a flux of phi A crossing a region of space where there are B type particles with NB particles per unit volume. Okay? So, this is my given problem, and then I ask the question that can I sort of find the interaction rate per unit target particle if I am giving that A type of particles with flux phi A is hitting with NB particles per unit volume. Then the question that I am asking, that what will be the interaction rate per unit target particle. Now, I would like to say that this can be said as R A if that is the interaction rate per unit target volume. This will be proportional to two quantities, of course, the flux which we defined as phi A, and then there is another quantity which I will call sigma, and this is precisely what we called the cross section. Okay? So, this sigma is what is called the cross section of this process, which characterizes what kind of interaction that we are probing, and of course, this is also proportional to the flux of the initial state particles or A type of particles. Okay? So, this is phi A. So, this is how you can parameterize. Remember that this R A, this interaction rate, this can in turn be related to the the rate of transition from state I to state F, which was given by Fermi's golden rule in the non-relativistic quantum mechanics. Okay? So, we will use that formalism to define the cross section eventually. Now, let us move ahead further and define that there are A type of particles moving with velocity V A. Okay? So, this is V A, and B type of particles are moving with velocity V B, and most often when they are colliding with each other, we assume that they are moving in the opposite direction. Now, I would like to ask another question, that suppose in time delta t, A type of particle crosses a region containing delta n type of particles of type B. Okay? So, what that delta n will be? Then I say, okay, because the relative velocity is V A plus V B, so the length that it covers is V A plus V B into t. If you look into this figure, this cross section is suppose A. Okay? Let me define it as A. So, therefore, how many delta n that you are going to expect? This will be, let us write it in this red pen, that this will be essentially A into V A plus V B into delta t, and then this is basically the volume, And how many particles of unit volume the bees have? This is by definition that we said that we have NB particles per unit volume, NB particles per unit volume. So, I will multiply this with NB, and that is going to define how many particles that A type of particles actually interact, how many B type of particles the A type of particles interact while they are colliding. Now, with this I would like to define what is the interaction probability. How do I define the interaction probability? I will say this will be defined by the effective total cross section area divided by the A, because this A that we talked about, this has no significance. Okay? So, therefore, what we are going to say that this delta P, the interaction probability will be the effective total cross section area divided by A. Now, how should I define it? This should be the number of particles that A faces of type B, which is defined by delta n, okay, into the typical definition of the cross section of this process sigma divided by the area A. Okay. So, this will be the definition of what you call the delta P or the interaction probability. This interaction probability you can also visualize by saying that this is the probability of an incident particle to pass through a region sigma drawn around each B type of particle. So, basically you can imagine that this sigma, the cross section, is nothing but this kind of hollow this thing which you are actually drawing around each of these B type of particles, okay, within this area A to define what is your So, this blue, or rather what I am now drawing, this is the area A, and what I am trying to say that in this one, this hollow one is defined by area sigma, and this thick dot defines the particles of type B. Okay. So, therefore, the delta P will be simply, if I borrow this expression of delta n from here and put it back in this expression in the delta P, what it will become? This is NB into A into VA plus VB into delta T into sigma by A, and you can see that this A cancels and gives you an expression which is like simply NB into VA plus VB into delta T with the characteristic cross section sigma. So, now we can come back to the definition of what we call the interaction rate. Interaction rate will be basically this probability, interaction probability per unit time, right. So, this will be defined by dP dt, and that will be given by NB into VA plus VB into sigma. Excellent. So, now we ask this question that for a beam of particles with Na particles in volume P, what will be the total interaction rate? And the answer will be very simple. This will be simply given by this rate multiplied by the total number of A particles, and that will be Na into the volume V, correct? Because Na is the density, multiply with the volume V, that will give you the total number of A particles, multiply that by the rate that we actually defined so far. So, let us write this quantity as we have found this expression above. Okay. So, let us write this. This will be Na into V into Nb into Va plus Vb into sigma. Now, I can rearrange this quantity a little for my benefit, and I can say this is Na into Va plus Vb into Nb into V, okay, into sigma. Now, each of these three quantities define three important quantities that constitutes what you call the total interaction rate. The first part is what we call the flux, and that was the definition that we actually had, which we called phi. Okay. Then there are number of target particles, and that is nothing but Nb into capital V, and then there is this cross section, and that is sigma. So, these are the three quantities which actually defines that if you have a beam of particles with Na particles in volume V, what will be the interaction rate with particles of type B if the cross section is sigma. So, in a sense your phi is defined as Na into Va plus Vb, and then with this the interaction rate is phi into capital NB, where capital NB is essentially small nb into the volume V into the sigma. So, this brings me to the definition of the cross section. I will rather say that the cross section is therefore the number of interactions per unit time per unit target divided by the incident flux. Okay. So, I divide by this capital NB, I divide by the flux from the number of interactions, and that is going to define my cross section. So, this is what the definition of the cross section therefore is: number of interactions per unit time per unit target divided by the incident flux. Let us now consider a specific reaction of the type A plus B going to 1 plus 2. So, A plus B are the initial state particles which I define by I, and 1 plus 2 are the final state particles which are defined by F. Now, interestingly, I would like to remind you that we said that we require quantum field theory to describe such kind of processes, because in quantum mechanics we actually do not have this provision of creating or annihilating particles. This is only possible in quantum field theory. We will look into some examples later. When we go to specific examples, we will give you more examples, but for the time being we do not go into the kind of processes that we are considering. Let us just focus on some initial state particle A and B are producing some final state particles 1 and 2. Okay. So, this is how exactly it is, and these initial state particles are coming with a velocity Va and Vb. You know, they are head on collisions to produce 1 and 2 kind of particles which are emerged at an angle theta, say for example. Now, let us try to once again write the interaction rate in volume V. How do I write it? So, this will be once again the flux into the number of target particle into the cross section, right. So, the flux into the number of target particles, number of target into cross section. So, this is something that we have learned so far. So, this is how exactly we are going to write. So, what is the flux? Flux is Na into Va plus Vb. The number of target particles is Nb into V, and the cross section is actually sigma. And as I said that this interaction rate in the volume V can be identified in non-relativistic quantum mechanics to gamma Fi, which is like giving you the transition probability from state I to state F. Okay? And of course, we have used that the flux is Na into Va plus Vb. So, in the non-relativistic treatment, once again to remind you that we are going to arrive to the relativistic expression which is actually obtained in QFT from the non-relativistic one. This is, so to say, is not absolutely the state of the art technique of doing it, but still it serves the purpose. It gives you absolutely the correct interpretation of the cross section. But if you want to do it in a completely quantum field theory way, then we have to actually treat the S matrix and actually derive the expression for cross section. If you want to look into the books of Peskin and Schroeder, say for example, this is done very nicely. So, you can look into that, or there are several other books also which does the job. But what we are going to do, that we are going to actually have this expression of cross section derived from the non-relativistic approach using Fermi's golden rule, the way that we actually derive it for the decay width. Okay? So, the first thing that we do is to normalize the wave function to one particle per unit volume. So, in that case you can say that this Na and Nb is simply 1 by V. So, this gamma Fi that we actually wrote, that will be Na into Va plus Vb into Nb into V into sigma. Now, for Na and Nb, we are going to replace that with 1 by V and 1 by V here. And you see in this process what we actually arrived to is that this V cancels and then we have Va plus Vb by V into sigma. So, this V, one of this volume in which we normalize, is remaining, but nevertheless we do not worry, because we have time and again said that this 1 by V factor cancels with the phase space normalization, which is also something that one has to take into account. And so, therefore, what we can do, that we can completely forget about the V, and we can say that this gamma Fi therefore can simply be written as Va plus Vv into sigma, and we remove all the unnecessary things from here. Or in other way, we can say that this expression of cross section can be obtained Fermi's golden rule to transition probability gamma Fi from the initial state I to final state F divided by this relative velocity factor, which is Va plus Vb. Let us remind ourselves of the transition rate using Fermi's golden rule. What the expression was? It was saying that gamma Fi will be related to 2 pi into T Fi square, where into rho Ef, where rho defines basically the phase space density, right, evaluated del n del Ef evaluated at Ei, and T Fi square is the transition matrix element square. Now, what is the phase space density? The phase space density del n del Ef, if you remember that this can be dressed up into a delta function, delta of Ei minus Ef into dn, and this dn, the phase space density, this can be written as pi equal to pi I equal to 1 to n minus n d cube pi by 2 pi whole cube. This is for a n body final state. Okay? And this can be written using a delta function, delta cube of Pa minus Pi, okay, where we invoke this condition of momentum conservation, and then this actually reduces to this expression, that this is 2 pi whole cubed into pi equal to I to n d cube Pi by 2 pi whole cube into delta cube of Pa minus Pi. Okay. So, let us try to put this expression back into the expression of the cross section, or rather the transition matrix element, okay, or rather the transition probability from state I to state F using Fermi's golden rule. So, this 2 pi whole cube will actually be conspiring with this additional factor of 2 pi which you have, and brings you this 2 pi whole to the power 4, and then we have T Fi mod squared, and then what are the other terms that we actually have? We have this delta of Ei minus Ef, which we can say Ea plus Eb minus E1 minus E2, right, into delta cube of Pa plus Pb minus P1 minus P2. Once I have written all the delta functions correctly, both the momentum and the energy, what I am left with is the phase space parts, which are d cube P1 by 2 pi whole cube into d cube P2 by 2 pi whole cube, correct? Okay. So, this is what we have for the process A B going to 1 plus 2. Now, if this is the gamma Fi, what will be the sigma A plus B to 1 plus 2? It is easy, because we have already seen that sigma will be gamma Fi by Va plus Vb. So, therefore, this will be 2 pi whole to the power 4 divided by Va plus Vb into integral of T Fi square delta of Ea plus Eb minus E1 minus E2 delta cube of blah 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 with this phase space factors. Now, if I go to the Lorentz invariant description of the normalization, then how this TFI square is going to relate it to MFI square? Remember that we said that the Lorentz invariant way of normalizing the wave function is to invoke a factor of 2e whole to the power half for each of the wave functions. So, therefore, for this one it is basically going to be a factor of 2EA, 2EB into 2E1 into 2E2, correct. So, MFI square, that is going to be equated to TFI square in this particular way with the factors of the energy. Now, therefore, if I want to replace this TFI square in this expression of the cross section with this Lorentz invariant MFI square, then how this expression is going to be? What I am going to do, that I am going to retain the expressions of VA plus VB in the expressions of cross section that as I had before, VA plus VB, and then I will also bring out these factors of 2EA, 2EB, because they are not going to be the part of the integration, and then I have replaced this TFI square by MFI square, and what I am going to do, I am also going to note that 1 by 2 E1 and 1 by 2 E2 in the phase spaces. And you remember very well that these are the expressions of what we called the Lorentz invariant phase space. This is called D of LIPS, okay, the Lorentz invariant phase space expressions, and MFI square is the matrix element which you can calculate from the S matrix for a particular process, and which we are going to do. And then we have this factor sitting down in the expression of cross section, and this is what is the flux, 2EA into 2EB into VA plus VB. And the question that you would like to ask is that, is this flux Lorentz invariant? And I am not going to take you through all the steps here, but rather going to bring you to the final expression of this F, that you can actually rewrite these terms nicely into a manifestly Lorentz invariant form and show that this flux which did not look like it is a Lorentz invariant quantity, this is 2EA into 2EB into VA plus VB, but it nicely gives you an expression of the form that 4 into PA dot PB, where remember these are essentially the 4 momentum associated with the initial and final state particles, and remember from our exercises that a scalar product of the 4 momentum is always a scalar which does not change with the different inertial frames. So, therefore, this is a Lorentz invariant quantity, and of course, minus m a square minus m b square, these are essentially the masses of this A and B type of particles, and this is also Lorentz invariant. So, this expression 4 into P a dot P b minus m a square m b square whole to the power half is Lorentz invariant for sure, but I suggest you that you go through the steps and do this exercise. Okay? But with all this, we arrive to this expression that this d sigma, the differential cross section, is nothing but it constitutes with 3 different parts, very important ingredients. One is the Lorentz invariant matrix element square MFI square, one which is the Lorentz invariant phase space part, which I call DLIPS, okay, Lorentz invariant phase space, divided by the flux factor which is sitting below, which is also Lorentz invariant. So, the differential cross section d sigma, this is actually Lorentz invariant. Okay, so let us evaluate the scattering cross section in the center of mass frame. Once again, for this process A plus B going to 1 plus 2. Now, what is the definition of the center of mass frame? Remember, when we talked about the decay, we said that the decay happens from the rest. So, that was the definition of the center of mass frame there. Now, in the case of scattering, the definition is as follows, that we have to have Pa is equal to minus Pb, and let us call that something like Pi star. Okay? So, basically in the center of mass frame, the momenta of the incoming particles are equal and opposite. So, that is the definition. So, now Pa plus Pb has to be equal to P1 plus P2 from the momentum conservation. So, P1 plus P2 must then also be equal and opposite. So, it must therefore be like P1 is equal to minus P2 is equal to some Pf vector star, and of course, we understand that it is not necessary to have Pi star equal to Pf star, it can be in principle different. Now, in the center of mass energy frame, therefore, the addition of the 4 momenta, Pa 4 momenta plus Pb 4 momenta, we can write it in the component like this will be Ea plus Eb comma Pa vector plus Pb vector. Now, in the center of mass frame, Pa vector plus Pb vector is equal to 0. Okay, and Ea plus Eb we can write that as Ea star plus Eb star, and what we are defining that this is actually equal to square root of S. This is what is defined as the center of mass energy, and the definition of S is essentially Pa plus Pb 4 momentum whole square. Okay, and this is one of the Mandelstam variables. We will discuss some other Lorentz invariant Mandelstam variables in our tutorial exercises. Now, let us look into the Lorentz flux F in the center of mass frame. From our definition, this is for Ea Eb into mod of Va minus Vb, correct. So, in the center of mass frame, we can write them as Ea star Eb star into Va star plus Vb star. Now, what we can do that we can write this, you remember that P is equal to mv, right. Now, in the H cross equal to C equal to 1 unit, m is having an unit of E. So, you can write it like P is equal to EV. So, therefore, what you can do that you can replace this Va star by Pi star by Ea star, and similarly Vb star by Pi star by Eb star. Now, therefore, what you see that Ea star Eb star in the denominator cancels, Pi star you can actually take as a common, and what it turns out to be 4 Pi star into Ea star plus Eb star, and this Ea star plus Eb star is nothing but the square root of the center of mass energy, or rather square root of S, which is called the center of mass energy. So, therefore, 4 Pi star into square root of S. Now, let us actually rewrite the scattering cross section in the center of mass frame. So, from the definition that we have obtained, it is 2 pi whole to the power 4 by the flux factor, which is 4 Ea Eb into mod of Va minus Vb into the integration of mod of Mfi square, the delta function on the energy, the delta function of the momentum, and then you have the Lorentz invariant flux factor d cube P1 by 2 pi whole cube 2E1 d cube P2 by 2 pi whole cube into 2E2, right. So, in the center of mass frame, now what you can do that you can trade off the flux factor to be 4 pi Pi star into square root of S as we just derived above, and then inside the integration this delta function of Ea plus Eb minus E1 minus E2 turns out to be, so Ea star plus Eb star, which is square root of S minus E1 minus E2. So, this is the delta function on the energy, and just because Pa plus Pb is equal to 0, so delta cube of Pa plus Pb minus P1 minus P2 simply turns out to be delta cube of P1 plus P2. And these 2 pi factors we have actually adjusted to a whole factor of 1 by 2 pi square. So, therefore, that leaves us with these factors like d cube P1 by 2E1 and d cube P2 by 2E2. Now, what we have to do that we have to basically perform this integration. But remember that we have actually encountered such an integration while calculating the decay width and using the properties of the delta function. And what was that? For the calculation of the decay width, we had an integral of mod of Mfi square delta of Ma minus E1 minus E2, delta cube of P1 plus P2 there also, with this Lorentz invariant measures d cube P1 by 2E1 into d cube P2 by 2E2, and it turned out that the integration was actually coming out to be mod of P star by 4 Ma into integral of mod of Mfi square into d omega square. So, therefore, we can say that without doing this integration in explicit, using this previous result, we can say that mod of Mfi square delta of square root of S minus E1 minus E2 into delta cube of P1 plus P2 d cube P1 by 2 E1 into d cube P2 by 2 E2, this integration will turn out to be what? I will say that this is mod of Pf star, say for example, the final state momenta. In the denominator, instead of ma, we will have a square root of s. That is it. So, with this, then we can write the final form of the sigma that we actually obtained. So, this is 1 by 2 pi whole square, then the flux factor 1 by 4 pi star, let us put a mod here, into square root of s, right, and then this factor mod of Pf star by 4 square root of s integral of mod Mfi square d omega star, right. So, if you kind of adjust these terms a little, this will turn out to be 1 by 64 pi square s mod of Pf star by mod of Pi star Mfi square d omega star. So, this is a very famous formula for scattering cross section in the center of mass frame. So, once you can evaluate this mod of Mfi square from your fundamental theory, then you are able to calculate the cross section for 2 going to 2 process in the center of mass frame. You can also do the differential cross section in the center of mass frame. This simply comes out to be d sigma d omega star, that will be equal to 1 by 64 pi square s mod of Pf star by mod of Pi star into mod of Mfi square. One thing that you should note, that this quantity d sigma d omega star is not manifestly Lorentz invariant, simply because of the fact that this Pf star and Pi star, these are specific to the center of mass frame, right. So, therefore, and also d omega star that you actually have is also a frame dependent quantity. So, the differential cross section is not Lorentz invariant. So, a Lorentz invariant differential cross section can be defined in terms of d sigma dt, which turns out to be 1 by 64 pi square s mod of Pi square in the denominator with mod of Mfi square, and this is something that we are going to do in one of our assignments. Okay. And you can also derive what is this mod of Pi star in terms of the center of mass energy, or S, and MAMB, and it turns out that this expression turns out to be mod of Pi star equal to 1 by 4 S in bracket S minus MA plus MB whole square into S minus MA minus MB square. Okay. So, this is something which we are also going to do. So, one of the famous examples which we will carry out later is E plus E minus going to mu plus mu minus. So, it is a pair annihilation of electron positron to create a pair of muon and antimuon, and in this particular case, if you want to express the d sigma d omega star in the center of mass frame, this will simply read from this above formula, that 1 by 64 pi square s p mu star by p e star into mod of Mfi square for E plus E minus going to mu plus mu minus, and if you want to express the center of mass energy S, this will be simply E E star plus E positron star whole square, which you can say that this is 4 E E square, just because E E minus has to be equal to E E plus. Okay. So, as they have the same mass. So, therefore, this is something that we are going to explicitly work out when we find out how to calculate the matrix element square. So, with this we actually end this lecture on how to evaluate the cross sections, and we will proceed with some other topics in the next class. Thank you.